Hi everybody, this is Mrs. Weens and it's time for our note today on the properties of graphs of functions. So I also had you do some work with this, trying to come up with thinking about this on your own, piecing through it. Now I'm going to explain it to you in more detail. I will say that this video contains a lot of important concepts that will be discussed throughout this entire course. Okay, if you are able to understand these 6 properties, you'll be really far ahead because you won't have to memorize a lot of things. In fact, it's even better if you need to memorize what these properties are and then be able to apply them to any parent function, because these definitions that we talk about here are so important throughout mathematics, both in courses in high school and if you take anything after high school as well. So I started the note with just a few new notations for you. We start with the concept of infinity. So I shouldn't say math, numbers go on forever and ever and ever. So the concept of infinity is that concept that when we try to find a higher and higher number, we can be doing that forever. So that is denoted, you'll see here, by this kind of sideways 8. Okay. And a function can have an infinite number of x values, okay, in it, if its domain is restricted, and even if it's not. So if we have this here, x arrow infinity, this means that x approaches infinity, okay? So we're talking about as x approaches infinity, what happens to a function? That's going to come up later. You can think about it in normal layman's terms as what happens when x gets really, really large. So when you start putting extremely large numbers into the function, what happens? So think about like a million. If you put a million into the function, where would it be? Okay. Then the negative, x approaches negative infinity. So x arrow negative infinity means as x approaches negative infinity. So that's as x gets very, very negative. So you get really, really far into the negative. So think like putting in negative a million into your functions, what's happening. So if you have a function, you can think about x approaches infinity as what happens as you go further and further and further and further to the right. And x approaches negative infinity is what happens as you go further and further and further to the left, visually when you're looking at a function. Okay, so that's infinity. And then we get into interval notation. Okay, so now, as of now, we've been using something called set notation. So this is set notation. So when we're talking about domain and range, you need to be able to be familiar with either interval notation or set notation, okay? Because both, in the world of mathematics, both are used, not really even for any particular reason or other, it's just they're both used. So we need to get familiar with that. So if you look at this example, these two things mean the same thing. So x is in the set of, okay, so that weird E means in the set of, okay? So x is in the set of da-da-da-da. So when you see these examples down here, x is in the set of 2 to 4, 0 to 10, 2 to infinity, negative infinity to 5. There's a difference if you're using round brackets or square brackets. So round brackets means that the numbers themselves are not included. So x is in the set of round bracket 0, 7 round bracket means that x is in the set of all numbers between 0 and 7, but not including 7 themselves, 0 or 7 themselves. So in set notation, we would say x is greater than 0, but less than 7. So these two things mean the same thing. Square brackets, on the other hand, mean that the numbers themselves are included. So x is in the set of square 2, 4 means all numbers from 2 all the way up to 4, including 2 and 4 in that. So that would be the same as you would have 2, and then you would include the little line there to show greater than or equal to 2, and less than or equal to 4. Okay, now you might have a combination. You might have a square bracket on one side and a round bracket on the other. So when in doubt, it's always going to go smaller number to larger number. So you put x in the middle. Okay, so 10 would go here and 0 would go here. But the 0 would include the little line because 0 is included. So x is greater than or equal to 0, but less than 10. So 0 is included, and then all the numbers up to 10, but not exactly 10. Okay, let's think about this. 2 to infinity. So if you think about a number line, sometimes that helps as well. If we have 2 here, basically we're including 2 in what's in our number set, and we're going up to infinity. So how we really write that in set notation is that x is just greater than or equal to 2. We don't write between 2 and infinity because we can't write less than infinity. That doesn't make sense because infinity is not a number. Okay, x is in the set of negative infinity to 5, but that's a round bracket, notice. So you pause the video and try this on your own. Are you doing it? Okay, so draw a number line to help you. You have 5, and then you don't include 5 and any number before 5. So really this is just x is less than 5. So any numbers from negative infinity, as negative as you want, anything up to 5, but not including 5. So again, this one had the square bracket, which is why I did the inclusion, and this one has a round bracket, which is why there is no inclusion. So you will be asked to do a few questions to practice using this notation because, again, it can be used interchangeably in questions that come up or on tests or exams, and you'll be expected to use either notation. Okay, so we're going to go over 6 properties today. It is essential that you know all 6 properties. You will be having a quiz where I just give you 2 functions and say discuss the properties of these functions. I don't name what the 6 properties are. You'll be expected to know what the properties are, okay? And you'll be expected to then discuss, of course, what the properties are of that function. So these first 3, I include, they're short because I think that you should all be comfortable with them. Okay, it's the last 3 that are new and a bit more confusing. So for any function, you'll need to be able to talk about the domain and range. That's just one property, domain and range together. So for instance, name the parent functions for which the domain is x is in the set of all real numbers. Well, the first parent function is the linear function, and that has a domain of that is that way, so I can include that. Then I think quadratic, yeah. You can put anything into its domain. Square root, you can't because you can't square root a negative, so that doesn't work. 1 over x, that doesn't work because you can't put in 0. What about 2 to the x? That works. You can put anything into 2 to the x. Sine x works. And then our new one, absolute value of x, that also has a domain that matches that. Just making sure, yep, I got them all. Okay, so you'll be asked to answer questions about domain and range as expected. Intercept, so that includes the x and the y-intercept. Again, that's just one property. So remember, x-intercepts, you just set y equal to 0. And the y-intercept, you just set x equal to 0. Okay. So for example, name the parent functions who have a y-intercept of 0, 0. So another way of thinking about this is they pass through the origin. So my linear, I just kind of go through them in order in my head and just say, are they good or not? So yes, linear. No. Yes, quadratic. Yes, square root. No reciprocal, because that's an asymptote. 2 to the x does not, because at 0, 2 to the x is at 1. Sine x, yes. And absolute value, yes. So there we go. You will also be asked just, is a graph continuous or not? Okay, for the most part. And how do you know, or whatever. A continuous function basically is just a function that has no holes, jumps, or breaks. So just think about it that if you were drawing that function, you would be able to draw it without taking your pen off the page. So something like a reciprocal is not continuous because it would be like this, and then, oh, I have to take my pen off to be able to draw the rest of it. Okay, so that's what continuity is. So often I'll use CTS to say that a function is continuous, and CTS to say that a function is discontinuous. So a function is continuous if it has continuity. It's discontinuous if there's any hole, jump, break, asymptote, anywhere where you'd have to lift your pen off the page. All right. So like I said, those are the first three, and I encourage you when you're examining a function to just get those out of the way first, because hopefully they're the most common or the most familiar. Sorry, that's the word, familiar to you at this point. So now we need to think about the intervals of increase and decrease. So I'm going to make a little function here. It's not very exciting, but you know, I'm going to, okay, so label of negative, this is going to be -2, -1, 1, 2. It's important that we get all on the same page here. From 2 over, it's going to be a horizontal line. Okay. -2, you're going to have like a maximum here. At 1, you're going to have a minimum down here. Okay, and then we're just going to kind of go, woo. I'm just making this up to kind of to be able to discuss what intervals of increase and decrease are. Okay, so this is just a generic function. Okay, it looks like a sine curve then together with a line, a horizontal line. That's allowed, that's okay. So to talk about this, we're going to create our little friend, Pierre. Okay, Pierre is a mountain climbing ant, and you're about to see my awesome artistic skills coming through. Look at that, Pierre. Now, Pierre has a special condition where he can only move left to right, okay? He can only move left to right. So if he's here on the function, he can only keep going this way. He cannot go in this direction. So he can only move left to right. I cannot stress that enough, people. He can only move left to right. So when you're looking at intervals of increase or decrease, you're always looking left to right. Some people want to start at the middle, at the y-axis, and then they want to look this way, and then they want to look this way, but not intervals of increase or decrease. You got to start left and move right. So if Pierre is climbing, then the function is increasing. So here he's going up, 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 up. So here the function is increasing. Okay. If he is taking a nice little ride down the, I got his antenna on the other one. Here he is sliding down the hill. Whee! Okay, if he is falling, that means the function is decreasing. Okay, now if he is just walking along at a common pace there, he's neither increasing nor decreasing. In fact, here at the maximum, he's not increasing or decreasing, nor at the minimum. Okay, so that's Pierre. It's pretty good artistic skills there, I would say. So if Pierre is climbing up, then that means the graph is increasing. So that basically looks, we would say about that graph up there, that f at x is increasing, so you can just use an up arrow on the intervals -infinity to 2, sorry, to -2, and also 1 to 2. Okay, so if you go back up So the function is increasing from here, so negative infinity, it's been increasing this whole time until it gets to -2, and it's increasing again from 1 to 2. All right, notice that I'm using round brackets because it's not actually increasing at -2. It's neither increasing nor decreasing there. Same thing at 1. Okay, so then if Pierre is falling, our graph is decreasing. So that's going to be between -2 and 1. Our function is decreasing. So f at x is decreasing. So again, you can just do a down arrow on decreasing on -2 to 1, the interval -2 to 1. Okay, so when Pierre is standing, so something like this, either he's at a minimum or he's on a maximum, or he's on a horizontal line. He is not increasing or, oh boy, he is not increasing or decreasing, okay? So he's doing neither. So I'm going to leave something for you guys to try, an opposite activity, okay? I want you to try to do a function that matches this description. So f at x, I want you to have f at x increasing from -1 to 3. And then I want you to have f at x decreasing from -infinity to -1 and 3 to 5. Okay, so try that out and show me what you have next class, and I'll see if you got that right. Okay, now we move on to symmetry, which is probably the most, often the most complicated concept. So before I talk about it here, I'm going to go over to a website called Visual Calculus. So you might want to take down the URL here. It's archives.math.utk.edu/visual.calculus. Okay, and you might want to bookmark this page for use later. We're going to go into pre-calculus because we're not there yet, right? And you can notice here there's an introduction to functions. You can check that out later. Polynomials, rational functions, but we care here about even and odd functions. So let's check this tutorial, okay? So a function f is even. Actually, I'm not going to read that. Let's just do this demonstration here. And you're welcome to go do this on your own as well. So the graph of a function f is symmetric with respect to the y-axis if the graph on f on one side of the y-axis is the mirror image of the graph on the other side. So here is a graph of a function which is symmetric with respect to the y-axis. So here's the y-axis. So if you put a mirror on the y-axis, this would reflect perfectly. It would be symmetric on the y-axis with respect to the y-axis. Hence, if the point P, which we could call xy, is on the graph, then there's a mirror image called Q on the other side of the y-axis. So I want you to think about, if this is xy, then what would this point be? If this is xy, what would this point be? For Q to be the mirror image of P, it is required that P and Q should lie on a line perpendicular, and that's the same distance from the, so what this basically means is that P is the same distance from the y-axis as Q is from the y-axis. So if P is xy, then Q would be -x, y. Okay, so they would have the same y value because they're on the exact same height. But whereas this x value, we're denoting x, this would just be the negative version of x. So there's 2 points that are symmetric there. So since y is f at x, then this means that f at negative x is equal to f at x. Okay, so this little prime stuff, that gets a little bit confusing, but I'd like the visual for you here. So if you put x into a function, f at x, you'll get y. And if you put the negative value, the same negative number in, f at negative x, you'll still get the same y. So for instance, if I put 5 into this function, let's say this is an x value of 5, I would get, let's say, 3. And if I put in negative 5, I also get 3. If I put in 1, I'll get, I don't know, 2.5. If I put in negative 1, I'll also get 2.5. So that's why f at x, if I put in x, is the same thing as f at negative x, because I get the same thing if I put in the negative value of that x. Okay, so there's the conclusion. And we'll get to that in the note. Now here, so that's what an even function is, what we just talked about. Symmetric on the y-axis. But an odd function is symmetric with respect to the origin. Okay, so I'm just going to press back so you can see that animation again. So this is something with a rotation of 180 degrees would be, so basically it's if I flip this up once and over once. So I flip it on the x-axis and I flip it on the y-axis, I would get to another point. So it's symmetrical with respect to the origin. Okay, so if P is a point on F, then there's another point Q, which is obtained by a rotation of 180 degrees. Or you can think about it as a reflection up and a reflection over. You'd get to Q. So now I want you to think about if P is denoted by X, Y, then what would Q be denoted by? Okay, so we can think about if P is X, Y, then Q would be negative X, negative Y. Okay, so because it's been flipped twice, both X is negative and Y is negative. So let's say if this is 5, negative 2, this would be negative 5, positive 2. Okay, so that means that if you take f at negative x, that's the same thing as taking negative f at x. Okay, so whether you make x negative or y negative, you'll get the same thing. Okay, now I do know that this is a bit of a confusing concept, so let's do the formal note about this, and hopefully that helps. The even one is a bit more intuitive for you to understand. The odd one's a bit stranger. So functions can be even, odd, or neither. Even functions are symmetrical about the y-axis. So let's say we have our most famous even function is y equals x squared. I'm going to try that again. Okay, this is just our classic even function. Okay, so if you put in a value of x, you get up to y. And then if you put in that same value in the negative side, you'll also get up to the same y. Okay, so x gives you y, and negative x gives you that same y. So therefore, f at x is equal to y, and f at negative x is also equal to y. So therefore, f at x is just equal to f at negative x. Okay, so that is what an even function is. Okay, so examples, x squared. So f at x is equal to x squared. If I wanted to find f at negative x, I would just put a negative x and square it. And negative x squared is actually just x squared. So aha, that's just the same as f at x. So therefore, that's an even function. okay? Notice that I did this with the function, not like I didn't just try a number and see if it works. Okay, to show something's even, you actually have to make sure you're using the function, not a point on the function. So let me test if this function is even or odd. So it will be even if when I find f at negative x, I get back to this exact same thing. So I put in negative x squared minus 4. So negative x squared is also just x squared again, minus 4. That's the same thing. So therefore, it's an even function. But what about this guy? So let's put in f at negative x. I get negative x all squared plus 7 times negative x plus 1. So that gives me x squared, good so far. Oh, but negative x times 7 is minus 7x plus 1. So that does not equal our initial function. So therefore, it's not an even function. Okay, so that's how you check if something's even. Now to check if something's odd, you see if it's symmetrical about the origin. So a classic example here, well, the linear function is, but also the reciprocal function is an odd function. Because if you put in a value of x, you'll get y. And if you go over that same amount in the negative direction, negative x, you'll get the same amount this way as you did this way, so you get negative y. So for instance, if I have 1, 1 in this function, on this side of it, I would have negative 1 over here. Okay, so xy and negative x, negative y are on an odd function. So if f at x equals y, and then f at negative x gives you negative y, therefore f at negative x equals just negative f at x. So that's the important conclusion you need for an odd function. So if you go to the next page, there's a few examples. Okay, so for instance, 1 over x. So if I find f at negative x, so that's 1 over negative x. Okay, so I put the negative down there where the x is, which is what that tells me to do. So really, though, that's the same as writing 1 over x, right? And negative f at x is just negative 1 over x. So therefore, f at minus x is equal to negative f at x. So therefore it's odd. Okay, 2x, f at negative x is equal to 2 at negative x. So minus 2x. So notice they're not even because they're not the same. So now I'll check f at negative f at x, which is just negative the function 2x. So minus 2x. So look, this gives the same result. So f at negative x is equal to negative f at x, and therefore that's an odd function as well. Now, what about sine x? Okay, is it even or odd? So let's draw sine x. Let's see if I can. It looks like this on this side, right? And on this side, it looks like this. So it's not even because if you go this way, it's not symmetrical, but it is odd because if I were to go flip this way and this way, I get back, then it works, right? Up and over. Okay, so it looks odd, and it is odd, in fact, but why is that true? Okay, basically, if you were to try to do this normally, let's do f at negative x. That would be finding the sine of negative x, okay? Now, I can't just take this negative and throw it outside of the sine function because remember, this is an argument, the sine of negative x. So it's not multiplication. I can't move the minus 1 around. negative f at x is minus sine x. So these look like I should be able to just rearrange, but that's not enough logic. So I got to go to my definition of sine on the Cartesian plane. So recall that sine is just if this is theta, and this is y, and this is r. Remember that sine of theta is just equal to y, okay? Because we're going to let r equal 1 in the unit circle just to make things simpler. So if we take the sine of negative theta, remember to go negative, you just go in the other direction, we would get, because r would still be the same length, we would just get minus y. So sine of negative theta is equal to minus y, which is exactly fulfilling what an odd function is. So this is saying that f at negative theta is equaling to negative f at theta. So therefore, it's odd. But you kind of have to show it on the Cartesian plane. So if this is all confusing to you, please, please, please highlight it, put a star. I'll explain it again in person. I'll show a few more examples. I'll do it in a different way because it is important that you understand even in odd functions. You can try watching the video if maybe I was just going a bit too quickly. But if the explanations didn't help, I'll try a few different ways for you. This is super duper duper important though, because I often have students doing this wrong. On the test, I will ask you, is this function even or odd? And what you cannot do is put in specific numbers. So if I give you a function like something really weird looking, okay, you can't just say like, oh, let me just put in like 1 and see if it spits out the same number, whether I put in 1 or negative 1. You can't do that, okay? You have to actually do what I did and put in negative x and do negative f at x and f at negative x and compare them, okay? So you find f at x, which is usually given to you. Find f at negative x and then negative f at x and see if there's any any equalities. So think if these two are equal, then it's even. And if these two guys are equal, then it's odd. And if none of the three of these are the same, then it's neither even nor odd, which happens too. Okay, so our last thing, phew, this is a long note, I know, is end behavior. So end behavior asks the question, as a function gets close to infinity, what is happening to the function? So you know how I'm always so annoying and tell you make sure you draw your arrows on your functions? This is why, right here, folks, is because they help you to determine the end behavior. So if you think about a function, like let's say you're going to be, this is a cubic function, we're going to be getting into those next chapter. You would be looking at what is the function doing as x is approaching infinity, and what is the function doing as x is approaching negative infinity, okay? So remember that increase and decrease, you are always looking left to right. Well, end behavior, you're looking out to the right and then out to the left, so it's different. So if we say, if we say as x approaches infinity, y approaches infinity, that means basically at the end it's going up, okay? So going to the right, it's going up. If we say as x approaches infinity, y is approaching negative infinity, so as x is approaching infinity, that means it's going down in that direction, okay? If we say as x approaches negative infinity, so now I'm going to the left, everything you own in a box to the left, y approaches infinity, that means it's going up this way. And as x approaches negative infinity, y approaches negative infinity, that means it's going down as you go to the left. Now, what about if there's asymptotes? And you're like, Mrs. Weeds, I didn't leave room for this. I'm sorry, guys. I hope you did. If not, just get an extra piece of paper. Okay. Sometimes you can have an asymptote at, let's say y equals a, and it looks like this. So then you would say, as x approaches infinity, y is approaching a, that number, whatever it is. Okay. Or, of course, you could have it being this way. So as x approaches negative infinity, y is approaching a. All right, so that is end behavior. It's what is the function doing as it's getting really, really big to the right, going to infinity, and what's it doing when it goes really, really big to the left, so approaching negative infinity. Okay, and you use this notation with arrows to answer that, which saves you a lot of writing. Just one last example to kind of wrap up this note. So what transformed parent function would have the following characteristics? Sketch. So a domain on anything, okay, any real number, and a restricted range. So let's think of what would even have these two characteristics. Okay, not linear because it doesn't have a restricted range, but quadratic, hello, that has a domain of any real number, and it also has a restricted range. Absolute values in the same boat. Those are really the only two. So it's decreasing on negative infinity to 0, and so in other words, it's falling until it hits x equals 0. And then there's an increase from 0 to infinity, so it's rising after x equals 0. Now, what would that vertex be? Let's think about that. Well, it's going to be at 0. What's the y value, though? Oh, well, let's look at the range. The range is greater than or equal to -2, so that means that vertex must be -2. So here's my 0, -2. So it's either going to be a quadratic that looks something like this. That's really bad, sorry. Or an absolute value. So it's basically the same thing, just with lines. Okay? Something like that. Those are your two choices. Okay? Phew, that's a lot of learning to do in one video. Thanks for sticking with me, guys. And it's available for you as you need it, of course, as always. Thanks for watching. Hope you learned lots.